We have an assignment due tonight. And we had a video to watch before today. How did that go? Wanted to start with a bit of a discussion on it. So I guess my first question would be, what were your takeaways?
The contradictions, I guess, are just, it's odd to use a contradiction as like, this is why it is that this is proof because of the contradiction.
Mm-hmm.
I don't know, I was just watching it because first it was talking about the set of everything contained the empty set, and that's a contradiction. And then it was talking about mathematical contradictions and how using Euler's, I think. Not Euler's.
Oilers.
Or there's like little card setup stuff.
Oh, no, that would be girls. Yeah.
Gödel. Is it
Good.
Gödel?
It's like cursed.
It's German.
Yeah.
The own mouth.
But they were talking about the contradiction of like the card that contains P.
Mm-hmm.
It's like it's either the statement is either true or false.
Yeah.
It's not there, or it is there, but it just doesn't have proof.
Yeah, the proof for that was the logical statement on the card is there is no card with Gödel number G. And the number of that card was G.
Yeah. So I found those to be kind of just weird to think about.
Yeah, with the takeaway of just that is the proof that there are true statements that cannot be proven.
All because of the issue of self-reference.
Mm-hmm. Yeah, we started with the set of all things that don't contain themselves. And there's no place to place the set that doesn't contain, it's a set of everything that doesn't contain itself. Because if you put it in there, it doesn't belong in it. If you leave it out, it belongs in it. So that became a very big problem.
Then I think they said they tried to solve that by just limiting the set.
Yeah, that became a.
And then I think when you in context of the issue of self-reference, you mentioned the set of all sets not being a set. So what is it then, a function?
Yeah, and well, it wouldn't be. It's something that we can't. It's not something that you can reference.
They never gave it a name, did they? For that kind of set.
No. But it's something that we don't think about. We can't because it creates problem with self-reference.
I can understand the issue of trying to resolve it causing issues, but at the same time, not thinking about it also feels kind of unproductive because it's just pretending it doesn't exist.
Yeah.
If you pretend a train heading in your direction doesn't exist, that doesn't mean you're not.
Yeah, we can't completely ignore it, but we also can't incorporate it using our rules, using the rules of the system. So how do we account for that? It just becomes a paradox. I find that to be very interesting because there are true things we can't prove. It is suggested that it's possible the P equals NP problem is one of those. P either equals NP or it doesn't equal NP. But it may be possible, or maybe that we cannot come up with a proof for it. One of those is true, but it's unprovable. What else was interesting?
For me, the difference between completeness and decidability, that to be something that when I was watching the video, for some reason going into it, I thought those were the same thing. That something, when it's undecidable, it's like inherently incomplete, like in the sense that if we have like a Turing machine, like I thought that was not completeness, the fact that we can't say the contradiction, but I guess going into this video, it kind of explained to me more that completeness and undecidability were two different things.
Yeah.
Even though for some reason I had them sort of mushed together in my mind.
Yeah.
So
That makes sense. Completeness just being whether statements follow from the axioms, meaning that if, when you have an if-then statement, if you have all of the ifs, then we can prove the then. And it turns out that that's not necessarily always the case. There are true statements that we cannot prove.
I will speak another interesting part of that one. Pretty much any mathematical. I remember exactly what the problem, any mathematical system you have is gonna have like those holes. Proofs with no. Or no, statements with no proofs.
Conclusions with no proof.
Yeah,
Yeah.
that was kind of weird.
Something I couldn't understand was Turing completeness.
Yeah, I was gonna bring that up, but it didn't.
Yeah, it's just, I don't understand how they said that if something is Turing complete, it can calculate everything that. Like, it can be whole, basically, like
Yeah.
whether that's a programming language or if that's quantum mechanics, like I don't understand that.
That basically means that we can represent everything that we need to logically, which creates an equivalence between these systems. That means it has the components that we can break it down to emulate logic. So a programming language can be converted into another programming language because they are logically complete. So Turing complete just basically means that we can make if statements out of it. We can define loops within. We can break them down into their logical components in a way that we can reconstruct another system by coming up with an equivalence between breaking this down into its logical components, combining them into this logical system. But it's not just true across programming languages. Like you could write a translator between C and Java, but it turns out that you could also write a translator between the Game of Life and Magic the Gathering. And any other proven Turing complete idea. It's not necessarily proven exactly how we would do that because that would be very complicated. But it turns out that we don't have to. If we can use the two systems are Turing complete. That means that they can be broken down into that topic, which means that with enough work, we could reproduce the other system. Or emulate the other system. I like to think of it as emulation, rather. Does every Turing system have a Hall problem? Basically, if you're using any Turing complete system, you could use it to represent any recursive language, and it would have the same issues with any recursively enumerable language that you would have with Turing machines. It's a system like a Turing machine that you could use to represent everything that a Turing machine could. It's just not quite as nice as a Turing machine. I mean, imagine trying to use Magic the Gathering. If I said, here's this assignment that I'm going to give you, this next coding project, but instead of using a programming language, you have to define it using the rules of Magic the Gathering. That's all you have. It would be incredibly difficult, but according to this, it would be possible. It would take a lot longer than the rest of the quarter, but that's wild to think that you could, if we go back to your last project, make your CYK algorithm out of the rules of some other system, some other Turing complete system. Other thoughts on that? What did you think of the Game of Life and emulating the Game of Life?
Thought that was pretty cool, but I'm already a big fan of Game of Life.
It is a really cool system, but just the fact that it itself is Turing complete. Such simple rules can beget such complex results. You could code CYK in the Game of Life. You could make YouTube out of the Game of Life. You could watch the video explaining that YouTube can be emulated with the Game of Life in the Game of Life.
And in addition to the halting problem, there's the can this be done in a way that will resolve before the end of the universe.
Yeah, there's a lot of when we start talking about this, what is feasible becomes very far removed from what is possible. But it's always worth studying what is possible, because as technological advancements come our way, as we figure out how to do more things with fewer resources, more of that becomes possible. Any other interesting takeaways from the video? How did the halting problem fit into this? Did that help people understand the concept of the halting problem? Anyone want to take a stab at explaining the halting problem from how you understand its perspective?
I mean, I feel like the most basic thing to say is that if you have, I believe it's a Turing machine that has a state where you say, yes, it can halt, or no, it cannot halt. If you convert the yes, it can halt into an infinite loop, because we can do that, then we have this contradiction of if it enters yes, and it says that it can halt, then it'll enter an infinite loop and never halt. If it says no, it can't halt and halts, then that's contradicting the fact that it can't halt, it halted.
Yeah, we're asking the question, what does this machine do on itself? Which is that's the important part of that.
Yeah.
Is that we have to make sure that we're running its own source code. How does this algorithm perform on itself? If this algorithm halts on itself, then we necessarily go into an infinite loop, which is wrong. If we conclude no, this algorithm does not halt on itself, then we halt with the answer of no, and it's wrong. Yeah, so that's basically the halting problem.
One of the things that I previously had struggled with understanding related to this was the other day I asked about the yes or no Turing machine. The reason why I asked just because it felt by adding that loop, it seemed like it was moving the goalposts.
Yeah. So
But now I understand.
it makes sense. We don't have to make something a final state just because we could get there. We now just have added some construction beyond that, such that we will now infinitely loop and never reach finality from what used to be a final state. And then that is a legal construction that we could make. So because it is a legal Turing machine, and we want to be able to say the halting problem should work if we have an algorithm for it, it should work on any possible Turing machine. So this is a legal Turing machine that we could make, and it happens to be the exact Turing machine that we could use to force a contradiction. It means that it can't work for every Turing machine. Any other takeaways? Any other thoughts? Tying it back to anything that you've seen in any other class? Any other idea? Just things you were thinking about while watching it?
The idea of Gödel's numbers kind of reminded me of this video that I watched. I think it was what is plus times squared, which sounds kind of strange, but it's about lambda calculus. But it felt kind of like that, but in reverse.
Yeah. Yeah, I can see that. Yeah.
Oh, the natural versus real numbers, it made more sense, I think, the way it was explained here, even though you explained it the same way in class. That kind of making clear how the diagonal, as they're going down the diagonal, they're adding a new whatever place it is, tens, hundreds, whatever place, they're adding an entirely new number to that place for every single number in the
You're generating a new number that cannot be anywhere in the table because it is distinct from every number in the table at the place that you're changing the digit.
Yeah, so when you were kind of going over that the first time, I was like, what is he talking about? Here it kind of made more sense. So
Okay.
yeah.
the idea of that proof make sense to everybody else as well? Just how you can use that to show that this table is not complete? The proof by contradiction is assume that this table is complete. Even if it goes on forever, it is complete. Given a query of, is this number in the table, we can identify where it is in the table. Even though the table is infinite, you would need to be able to identify where a particular query is. And this process builds a number that becomes your query that is not in the table. Derek says the quote, future generations will remember set theory as a disease from which one has recovered. As academics used to say very profound, very silly sounding things. Any other discussion points? Are we ready to move on? So I think that video very nicely sums up very well just kind of the concept of the theory of computability. That here's why we think about these kinds of problems. It's worth knowing what we can and can't do. I think this is important as computer scientists go into industry because you may be tasked with a problem and you can determine whether that problem is solvable or whether that problem is solvable in a reasonable amount of time based on these kinds of abstract arguments. And you won't waste a bunch of time trying to implement something and then realizing that it takes forever to run, or that you got reasonably close, but there are these edge cases that we just can't account for no matter what we try. That's going to be a ton of wasted time. If you are able to identify that, then that is promotionary material. Those are the kinds of people we put in charge of things, because you can make important, informed decisions about actionable items based on a knowledge of in advance, will it or will it not work? I can give you the example. I think I've done this in office hours a couple times. One of our administrative, I'll say, it was our provost, said that we can get everyone on the same page and have AI solve our scheduling problems so that the entire schedule is made by an AI, given the associated constraints of when professors can teach, when the rooms are free, when prerequisite chains are offered, et cetera. And if you have the knowledgeable background, you know that this scales exponentially. It is NP complete. This is not something that in a reasonable amount of time, any computer system will return to us, given the scalability, the size of our university. So rather than waste a bunch of time and resources trying to get this process figured out, we just said, no, basically. No, and here's why. Let's come up with some other way of handling this. Let's not even investigate it because it's not going to work. And it saves everyone a time, because in the end of that, it's a waste of time to go down that road. All right, last time we were talking about the post-correspondence problem as a middle ground, a way of saying we can link the post-correspondence problem to the halting problem as one that is undecidable. So we want to, as we add these to our list of undecidable problems, we can now reduce into the post-correspondence problem instead of the halting problem as an end result for our undecidability proofs. And because of the post-correspondence problem, the way that it's set up, the fact that W1 and V1 are the beginning of two of these, this ends up being super useful when we go back to context-free languages and start non-terminals, because W1 and V1 can be basically S arrow whatever W1 is. That is the first expansion of the start non-terminal. And now we can have two different paths through the same grammar that produce the same string, but now we have two different paths that do it. One that goes S arrow, what produces W1, one goes S arrow, what produces V1. So we can make claims about context-free languages. So There is no algorithm for deciding whether a context-free grammar is ambiguous. And this is a proof we reduced to the post-correspondence problem. So when we talked about grammar ambiguity was a bad thing, and on an exam, I had to come up with an ambiguous grammar. It turns out that if you're given a grammar, there is no algorithm to decide whether that grammar is ambiguous. We can go through work that looks at that particular grammar and do some work to figure out whether it is ambiguous, but no generic algorithm exists where you pass it a grammar and it can say yes or no, it is ambiguous. It can either search for and find a derivation for a string, two different derivations for a string that come up with that. And when it finds it, then it can output, yes, it is ambiguous. But how do you answer no, the context-free grammar is not ambiguous? Since there are an infinite number of strings in the language, it will be ambiguous as to whether we will eventually find a string with multiple derivations or whether the grammar is in fact not ambiguous. Similarly, no algorithm exists for figuring out the intersection of languages defined by two arbitrary context-free grammars being the empty set. So basically, do two languages share no strings in common? If the answer is they share at least one string in common, maybe we will eventually find that via an algorithm. But if they share no strings in common and both of those languages are infinite, we've been working on this problem for a long time. We haven't seen any overlap. It's ambiguous between whether we will find some overlap eventually or whether there really is no overlap. And again, we can reduce this down to the post-correspondence problem because we will be building strings from the beginning of that. We're going to hard code the beginning of those strings as the same from whatever it is, one step away from the start non-terminal that we could generate, and then attempt to generate the same string from there. So that becomes the post-correspondence problem as well. Other conclusions that we can get from things like from our reduction proof idea. We have two grammars. Is the language of grammar 1 exactly the same as the language of grammar 2? Meaning that in the same way as is the intersection empty, we could say, do these grammars produce exactly the same language? As soon as we have an example of here's a string that grammar 1 can produce that grammar 2 cannot produce, we're done. We can answer they are distinct. They're not the same language. But so far, every string that we have put through either grammar 1 or grammar 2 has been able to be produced by the other one as well. Does that mean that they have the same language? Not necessarily. It means that we haven't looked deep enough to find a string that is distinct, or rather it is ambiguous between whether such a string will exist or not. We have two grammars. Is the language of grammar 1 a subset of the language of grammar 2? We can answer yes if we can determine a string in grammar 2 that is not in grammar 1. But if we haven't found that yet, and every string we've looked at in grammar 1 can also be found or produced by grammar 2, we don't know yet. It's ambiguous. If we have a grammar that is context-free, is it regular? Going off of a grammar, that turns out to be undecidable. We have two grammars. The first is context-free, the second is regular. Is the regular grammar a subset of the context-free grammar? That's undecidable. If we have a context-free grammar and a regular grammar, is the intersection of those two grammars the empty set? That's undecidable. But because of reductions, we have proofs for all of this. We know we can stop looking for an algorithm to decide this because no such algorithm exists. And that's what's so exciting about reduction proofs. I know I'm the only one who says that, or the only one who thinks that, but it's pretty cool. All right, we also should start talking about efficiency because we spent all of this time in data structures and algorithms talking about efficiency. And in this class, we haven't touched it at all. So everything we've said so far is fully honing in on the decidability question, not on the efficiency question. Because we cared about what is possible to do, not what is possible to do within a reasonable amount of time. However, depending on how you solve a problem via a Turing machine, how you represent things and the associated Turing machine construction, you can end up with very different complexities in the associated algorithm that you produce to solve that problem. Let's give you an example. The efficiency of deciding A to the n, B to the n on a single tape Turing machine. How have we solved that before? What did we do? It was the first problem that we had on a Turing machine. We're pretty close to the first one. We have some A's on the tape. We have some B's on the tape. We want to determine if they're the same number of A's as B's. How do we do that?
We paired.
Yeah. Yeah, we start on the far left-hand side. We see an A. We turn it into an X that says a seen A. We're going to move all the way past A's until we see a B. We're going to turn that B into a Y that represents that we've seen that B, and now we have a single X and a single Y that has paired the A's with the B's. We then go back until we see an X, move right, the next thing is an A, turn that into an X, and repeat that process. So breaking this down, we have two n moves to match a single A with a B. So we have A to the n, B to the n is the number of A's, and n is also the number of B's. It's not the length of the entire string, it's the number of A's. So we have to move past all of the A's as we find a B and then move all the way back to reset. So 2n moves matches a single A with a single B. So we have to do that for each of the n A's. So we end up with quadratic complexity of determining whether we have A to the n, B to the n on the tape. Now, instead of having a single tape Turing machine, what happens if we have a two-tape Turing machine? What is the complexity of the exact same problem on a two-tape Turing machine? How would we solve that?
Just n. You would just go through it one time and we'd go back the second time.
Yeah, so we would, for all the A's, we would be writing the A's on the second tape as we see them. And then when we see our first B, we're going to start going backwards on tape 2 and forwards on tape 1, matching the B's to the A's that we saw before. Yeah. So whole string is on tape 1, copy all the A's that we see to tape 2, then go backwards on tape 2, match each B that we see on tape 1 with the A's that we had on tape 2. And if we see a blank blank at the same time, we fall off the end of tape 1 moving right, fall off the end of tape 2 moving left, then we had the same number of A's as B's. We made a single pass through tape 1, which was n plus n, 2n, which is going to be complexity linear. It turns out by thinking about this, what we're really emulating when we have two different tapes like this is an element of parallelism. So if you're studying parallel programming or thinking about how many threads should I be making in a program to try to reduce the complexity of the program, you can really think about this in terms of one tape versus two tape Turing machines. So when you're thinking about the threads that are available to you and how you can utilize those threads to reduce the complexity of the problem that we're working with. Would having access to a second tape reduce the asymptotic complexity of the problem? If the answer is yes, then you can improve the runtime by turning an algorithm into a parallel algorithm. Any questions on that? I don't think we understand how exciting it is. We've reached compilers. After 7.5 weeks of the prerequisite material to be able to talk about compilers, we got there. We're ready to actually talk about what this class is supposed to be all about. Slide deck 19, the title of the course. All right, we're here. We have all of the background material. We can actually talk about what a compiler is, the steps of the compilation process, and at the end of this course, even though I won't make you go do it, you'll have the ability to go construct one of these. You'll have the background material to actually go write one. So, finally, this is the reason everybody took this class. They're like, this is interesting, or this is required, or this is the only class that fits in my schedule. And assumed we would be talking about compilers relatively quickly. But here we are. So we've talked about a little bit about what a compiler is, but the basic one-sentence idea of a compiler is we're translating a high-level language, program in a high-level language, into a program in a lower-level language, like assembly, like machine code, like bytecode. So we write code in high-level languages because it's easier for us to read, it's easier for us to write, it's easier for us to logically construct and map the syntax of that language to the logic that is the problem we are trying to solve. However, a CPU would look at a high-level language like this and see absolute gibberish in the same way that if you look at binary code, what you see is gibberish. So we need some translation service that is going to convert between the high-level language that we write in and the low-level language that a CPU can execute efficiently. So, have we all tried to write code in assembly in some prior course? How was that? If I had asked you to write the CYK program in assembly, how would that have gone? I see a lot of please don't make all the more insanity that Roller Coaster Tycoon was programmed completely in x86 assembly. If you haven't played Roller Coaster Tycoon, it's a little bit dated, but just go play the game and think someone wrote every line of this in assembly. And that still to this day blows my mind. But yes, low-level language is much harder for us to read and understand, but it is very much what a computer understands at a high level. So, do you note that assembly languages are still kind of a middle ground? This is not what a computer can still read, but it is a nice middle ground between the high-level language and the actual binary that a computer executes. Machine code is platform dependent, meaning that the binary that is run is different across different architectures. So depending on the architecture that you have, you need different assemblers that are going to assemble machine code into the target binary, which means that if we didn't have assembly language, what we would have is you'd have to write different compilers between high-level languages and the associated target architecture. So instead, what we usually have let's see, I don't really have a ton of space on this slide. Let's go to the next one. Yeah. We have our high-level language. We want to write a compiler into something like an assembly language. We'll call this x86. And then from here, we're going to have different assemblers I go into our target architectures. At least that's how I visualize this. And these assemblers are written for each of the assembly languages themselves. And this means that we don't, as a high-level language writer, we don't have to worry about compiling down into each of those different architectures. We only have to worry about writing a single compiler down into the assembly language. This saves us the work because this x86 is constant across all languages, all high-level languages. It's just a target middle ground. We write these assemblers once as a way to convert between x86 and the associated architecture. And the compiler now, we only have to write one compiler instead of writing a compiler down to here and a compiler down to here and a compiler down to here and to here for each language. All right. Questions on that? Because if we had to do this for Java and for C++ and for literally every language that exists, we would have so many compilers to write down to every possible architecture that this can be run on, that it's much easier. These stay consistent. So we should only write one of these, and then we can write one of these for each language down into each possible assembly language that we would want to be able to work with. Now, not every language compiles into assembly. Some work with bytecode. So Java compiles down into bytecode because bytecode is platform independent. And that's why Java is so widely used for platform independent code, because you don't need to worry about that middle ground. It creates its own middle ground and makes it very easy to write one piece of code that will run on just about any device out there. That's why Java is so popular. So don't write compilers for each possible endpoint. We could use bytecode as a middle ground. Program compiled into bytecode, platform independent. Bytecode is then run on a virtual machine. The virtual machine does the last step of converting this into machine code that runs on that machine. So let's think about what this process would actually look like. What do we need to do to convert between the characters that we type when we're writing a program and the end goal of binary that a machine can run in terms of its instructions? The process looks like this. We start with our source program. This is what we would write. This is your .java file. This is your .c file. This is whatever it is, whatever language it is you're writing in. The first thing we need to do is have a scanner. That scanner's purpose is to tokenize the program. We have a long stream of characters, and we need those characters to form the equivalent of words. These could be keywords, these could be variables, these could be symbols, but something that stands alone and has meaning. So if I have a variable that is foo, there's going to be the character stream FOO, and we want to combine that to say FOO, when combined together, is a variable that was defined earlier. We need the ability to replace this character stream with this idea of variable. In fact, this variable that was defined there. So tokenizing is going to combine together the program from being a sequence of characters to a sequence of tokens, and each one of those tokens can be looked up to have meaning. Variable, keyword, mathematical expression type, symbol. So once we have tokens, the tokens go into the parser. That's what you wrote for your CYK, is the equivalent of a kind of parser. The parser takes those tokens and says, do these tokens combine together in ways that produce statements that are productions in that grammar? So the parser can answer the question, is this sequence of tokens syntactically correct? given the rules of this language construction? If the answer is yes, then it will construct the parse tree for that program and pass that on to the type checker. If the answer is no, it will throw an error. And that's what comes back to you when your program crashes and gives you a syntax error. When it was in the parser part of the compiler, we came up with an error, and the parser is what returned that error to you. There was a syntax error in your program. Assuming the parser is successful, we're going to pass the parse tree onto the type checker. The type checker's purpose is to semantically validate the program. It's going to say, do we have type clashes? Do each of these statements actually have meaning? Can I execute the code that is in the statement? It is well constructed, but does that have meaning? Can I do what this statement requests me to do? The type checker works in kind of a top-down and bottom-up fashion at the same time. Top-down is going to be going from the beginning of the program, and it's going to be doing something like when you have a, let's actually write this out. Something like this. The top-down process is going to hit this line, and it's going to say, all right, I'm trying to store n as an integer, but it doesn't have the ability to evaluate this in place. It actually would have the ability to evaluate this in place. But if this was not 3 plus 5, but was like foo plus 5, what is foo? Is foo an integer at this point? Do we know exactly what is stored in this at this point? So top down is using, in looking at the definition here, to say what I'm expecting is an integer. And the bottom up process is evaluating from the bottom of this program. This is going to can go down in this and try to figure out, okay, I'm going to evaluate this process. And when it returns, what is the type of this expression? If this type ends up being an int, then we know we can assign int to int. And so this entire process evaluates as semantic meaning and gets the green light. On the other hand, if this evaluates and becomes something like a string, when the bottom-up process returns from this, because foo was declared as a string, then when we meet in the middle here, the expected value is an int, the given value is a string, we cannot assign a string to an int, so we would throw a semantic kind of exception, a type checking exception. So the type checker is doing this in the parse tree, and remember that a parse tree is kind of a depth first search type of. So we have one process that starts at the top that is looking for expected values, one process that starts at the bottom looking for actual values, and they meet in the middle where they can actually validate the type checking. So that's your type checker. From there, we pass the validated checked parse tree onto an intermediate code generator. The intermediate code generator is going to start looking at and making changes to your code. Between this and the code optimizer, the entire purpose of both of these steps is to improve the efficiency of your code, remove unnecessary lines, do things like refer to variables where they are, where it should be, rather than doing secondary lookups. It's going and optimizing the process to be able to run this code. It's making changes to the underlying binary based on an analysis of your code. And at the end of that, we basically have a map one-to-one to assembly instructions. So the intermediate code generator will take long, complicated lines and break them down into components that will map much easier to assembly instructions. And I'll give you an example of that. So, big overview. I go into each step in a little bit more detail here. So, as I mentioned already, the scanner reads the source code, identifies the tokens, the individual words. We have any number of characters surrounded by white space as the definition of a token. So if there's a space at the beginning or an end, or a tab or a new line, any of those at the beginning and end of a sequence of characters represents a new token. There's more to this in a lot of languages. Like you can imagine that a semicolon in the middle of a for loop, you don't have to have a space there. That there are certain languages that treat token separators a little bit differently. But in general, it's white space. Each token is assigned a type. So we need to know what type that token is. Is it an integer constant? Is it a keyword? Is it a variable? And yes, if the user hates white space, then it can be broken down further to figure out exactly where those are. Here's the example of a for loop line where there are many tokens in here that don't have white space, but each one of those tokens is assigned a type. Each one of those is made into a tuple, and then that tuple is passed onto the parser. We have a stream of token type tuples. What are the tokens and types here?
Would it be like some variable?
Yeah, some would be a variable. Equals is the assignment operator. Total would be a variable. Plus would be an operator. 10 would be an integer constant. Green variable if keyword 6.5 float constant, 87 integer constant. And you can see that the first line might be syntactically correct and semantically correct. The second one, not so much, but we're still able to, the tokenizer doesn't care about whether anything makes sense at this point. It's just trying to identify what are the token type pairs. Question for people, how would you implement a scanner? What that we have talked about this quarter, could be used to go implement that scanner. We want to analyze things character by character, right? To determine whether this is something that's been declared before. We would declare a variable somewhere in the program, and later on we would want to map and see, does this, it's the sequence of characters a variable that's already been declared. How could we do that?
If at this point we care about scope, then maybe a push down automata.
It's a good idea. Do we need the stack? What do we use the stack for?
The scope of the current
Gotcha. Yeah. Which scope are we currently in?
yes.
I think we're going to build different tables for that. So that's a great idea. But in fact, all we need is a DFA. We would build a DFA starting with the initial state being, all right, when we define a new variable, we're going to make new states that represent, like, let's say the variable was green. We'd have from the initial state, a GREEN final state. And that way we can pass an unknown string into this and say, does it already exist? We would reach a final state if it does. And when it does, that final state would be a lookup to its type. So final states recognize different tokens. Read in each token until a set of tokens is identified as a label of interest. Once we have that label of interest, we would do that. And we could build regular expressions for each valid token and then use regular expression syntax to determine, is what we are currently reading, is that already defined? Does that exist? Is it a keyword in the language? Yeah, for each token that we find, compare it to the possible regular expression until we find a match. So scanning uses regular automata. I guess we're basically out of time, so we'll have to come back tomorrow. But we'll talk about the rest of these sequences of steps. And actually dive into how we would make one of these. We had a little bit more time. What's coming next is looking back at the parsing process and coming up with a more efficient way of parsing. I have office hours starting now for any homework related questions. I will announce now that I will not have my typical office hours tomorrow, at least for a portion of it, because I am going to be in Tony's class playing the role of their boss. And it's a yellow. It's gonna be great.
Yeah, switch roles.
Yeah, yeah, he's doing his software engineering for cyber, so I'm gonna do what he did for me, pay him back for all of this wonderful, it's wonderful time as my client, client. I do have them today, so stop by with any more questions.